and we are going to be glad to move on. So karibu, welcome, or karibu sana to the class. And I have received requests in the past that I should not record my video. So for that reason, I'm switching it off. And therefore we can do the class. We went through the course outline and the schedule. I modified the schedule slightly because I also changed the content that I had planned to use to teach. So as you can see, the notes are quite enormous, but you need not to be worried when you see 282 pages, because of these 282 are so many examples that we will not need to go through like in class. You might need to go through them alone, and therefore they are more or less that was assist you prepare. And again, there is at the end of the lecture, or like at the end of the lecture notes, yeah, at the end of the lecture notes, they are actually about 20 pages of appendices. Let me show you. So appendices like the common integral formulas, the exponential and logarithmic functions, etc. So I just added them there because sometimes students are struggle to remember what was where or what meant what. And for that reason, I added sufficient amount of appendices to assist particularly in revision. And the one that are particularly important are the Fourier transform and Fourier series properties and formulas that we shall be going through at a later stage. So you can see that, of course, we will not be going through the Laplace. Laplace is covered somewhere else. But as I have mentioned, there are about 20 pages or so of common formulas, including the formulas for matrices that are filling up this material. So we will not necessarily go through all that material, but it's meant more or less to keep you without going to so many other sources to find relevant content. So today I will cover the content for the first week. But before I go there, let's see. I think there are some items that I thought I would mention. Yeah, so our course content remains as it was. Nothing can change it what we went through last week. The only item that I know I amended is that this. Oh, I'm not using that material. Sorry for that. So the only item that I guess I adjusted are the course. Where are they? Okay, we'll not have to waste time. I'm using two texts, both of them by the same person, which is this professor, Su. I think that is the pronunciation of his name. So the first one is dealing with the signals and systems. And instead of giving you the text, I just extracted the relevant pages that you require or we require for us to cover the material that we are to cover. So we are going to be using this as part one, and we are going to use this another book for the same guy called Analog and Digital Communication Systems, or I think Principles of Analog and Digital Communication, and it allows us to do the amplitude modulation and the angle modulation. So you will see them. We'll see that material later in the pages. I had purposed to include it in the initial pages, but I think I forgot. And there is some notes to the student that says that this material is assumed to have that you have a basic knowledge of calculus, along with some knowledge of differential equations and the fast circuits course in electrical engineering. So those are the obvious expectations that you should have. And we don't need to go through the entire material, but there is something that I guess I intended to say, or what I intended to say is in regard to the two texts that I have mentioned. So we will be covering this content for this first week. I don't intend to rush too much, despite we being late. So as we agreed last time, we are going to be meeting today. I actually prefer 3 p.m. because 3 p.m. people will have relaxed from the afternoon or lunch hassles, and by 3 they have settled. So I would rather we do 3 p.m. to 5 p.m. 2 hours are sufficient for one lecture. And then this is on Friday. And then tomorrow, which is Saturday, I hope that we can meet around 11 to 1 p.m. for another 2 hours of lecture. That should allow us to be to kickstart. So this again, we are going to consider it to be the first week, because last week we never did much. We only did the introduction. I never had enough material, and someone said that I should try to stick to teaching between Thursday and Saturday, and therefore we are going to stick to that. So today we are just going to cover the introduction to signals and communication, signals and systems, and do some classifications of signals. And of course, I need to attain one point. And if you have a question, you can always slide on chat, and I will be glad to respond. Let's keep our chat to formal communication, so that we don't have to interrupt one another with jokes or unnecessary comments that will just distract us. So having said that, I guess we are a good number. We are 16. I see we have not met. There are 3 people who are still not joined. But nevertheless, we are good to go. Oh yeah, and remember, these are the 2 books I had not realized where I put them, and I have actually put them in my notes. Therefore, I will also send you this in case you needed to look at them. They are done. They are text by the same author, so you can see it assumes outline of theory and problems of signals and systems by Wei Su, and the other one is analog and digital communications theory and problems by Wei Su. So these are the 2 books I intended to go through, or we are going to be using for the sake of this lecture. So having said that, we are ready to roll, and we start with the basic introduction to signals and systems. And we see now that the concept and theory of signals and systems are needed in almost all electrical engineering fields, and in many other engineering and scientific disciplines as well. So in this chapter, we are going to introduce the mathematical description and representation of signals and systems, and their classifications. So we also look at important basic signals. Of course, this will arise in lecture 2. So for now, we are just doing with the basic introduction and classification of signals. So the important basic signals that we use in communication, we are going to introduce them at lecture 2. So as an introduction, a signal is a function representing a physical quantity or a variable, and typically it contains information about the behavior or nature of the phenomenon. And for instance, in a RC circuit, the signal may represent the voltage across the capacitor or the current flowing in the resistor. And I think we can zoom slightly so that in case someone is using their phone, they can still watch. So as a matter of fact, we have seen that a signal represents a physical quantity or variable, and it contains information about the behavior of that quantity or variable. And we are giving an example of a signal in a typical RC circuit. And RC means resistor capacitor circuit, which we may have a voltage across the capacitor or the current flowing through the resistor. And we would want to characterize that signal. And we use mathematical representations to characterize them. I can see a question from Vitalis. Of course, Vitalis is asking if we can record, and if you actually look at the session is being recorded. So that is happening. I will be recording the lecture, and I will be sharing the recording via Google Classroom. Therefore, don't get worried about that. Okay. So mathematically, a signal is represented as a function of an independent variable, and that variable is time. And we normally denote a signal in this format, that is x of t is, of course, a signal. This is our signal that we represent as a function of time. So we start now with the general classification of signals. And the first classification that we do is in regard to whether the signal is continuous or discrete time. And we say now that a continuous signal, or a signal, is defined as continuous if t is a continuous variable. So we are saying that our independent variable t, it is the one that determines for us whether the signal is continuous or not continuous. And if t is continuous in time, of course, if t is continuous, then we consider that signal to be continuous signal. And if t is discrete, meaning it has finite number of variable, signal points. Yeah, I think I should say that. It has finite number of signal points, then it is referred to as a discrete time signal. And for illustration, you can see that this figure, at figure 1.1, describes a continuous signal as this one, and the discrete time signal as at the one that is illustrated at figure 1.1b. And of course, you can see that our function xt has a value at any point in time. So at time t, which might be 1.1767, as in a very high precision of time, you can get the value of our continuous function. On the contrary, the discrete time signal has a finite number of sequences that, beyond those finite sequences, if you wanted to find like the signal value at the point that I am pointing at, or these are the point 2 point something, 2.3 or 5.6 or -1.3, you cannot, that signal is not defined at that time. So the biggest characteristic is that with continuous time signal, at any one point, at any point in time, you can get a value for function of time, but for the discrete time signal, you can only get the value of that signal at discrete and finite discrete instances. So we have said that since a discrete time signal is defined at discrete times, a discrete time signal is often identified as a sequence of numbers, that are denoted by xn. So the xn, it could be a new term for you, but or a new expression for you. But this is how we express the discrete time signal, and n is always considered to be integer. So we never say that n is equals to 1.6 or 1.3, 1.73. So it will never be that. It will never be that. It will always be 0, 1, 2, etc., or 1, 4, 7, etc. So these numbers are considered to be the integers or integral. So illustration are given in figure 1.1 and figure 1.1a and figure 1.1b. So that defines for us the two classifications of signal as continuous in time or discrete in time. And I think a point to note is that it does not require, I think that is the last point I should mention, regarding the continuous time. It does not mean that t continues to infinity. No, doesn't mean that. It only means that for a given period, that the signal can always be, you can always get a value for a signal, for the signal that is continuous in time. But beyond some limit that you have set for yourself, the signal may go to 0, and therefore it may have, it will have a 0 value. So sometimes people may confuse that, saying that continuous in time means that it never goes to 0. That is not the case. It can go to 0, but we are saying that for the region in which it is defined, the function always has a value, and still the value can be 0, nevertheless. So I think that serves to introduce the discrete time and the continuous time. But let's see if there's anything else. A discrete time signal may represent a phenomenon for which the independent variable is inherently discrete. Yeah. And on the other hand, a discrete signal xn may be obtained by sampling a continuous time signal. So we're saying that we can be able to get a discrete time signal from a continuous time signal by sampling. And there are some rules of sampling that you will cover at a later stage. For now, we can just stick with that general expression that you can be able to obtain a discrete time signal from continuous time signal by sampling. And we are saying that if this is your continuous time signal, you can sample it at finite instances, and you get your discrete signal as expressed using this expression. So we are seeing same thing that yours might have been. We can say, for instance, that our continuous time signal x of t was defined as sine of t. But then if we want to find the discrete version of that signal, we can say that x of n will be given by sine of m of t. And we are saying that we are just m is integer, and t is the period of sampling. So in that case, as we go through the typical sine, we are simply saying we are capturing the values of that signal at finite instances, and that gives us so these finite instances in which we are sampling our continuous time signal gives us a discrete time signal that is expressed now in that form. So we understand that now x of n becomes a function of time, and I guess this equation right here illustrates that concept. And we are saying that x of n are called samples, and the time interval between them is called the sampling interval. That's something I've already mentioned. And when the sampling intervals are equal, then we define that as uniform sampling. So that serves for to introduce. Like I guess that is sufficiently adequate to talk about the two differences. And you're saying that now that a discrete time signal x of n can be defined in two ways. So we are saying that we have two ways in which we can define. We can define a discrete time signal in two ways. That one, using a formula like this one, or two, using a list of values, or a list of the sequence. So, so the first method says that you can say that, for instance, this expression right here says that if this is n is increasing, and the function of x of n, or the function of n, x of which is x of n, will have the value defined as for n is equals to 0, 1, 2, 2, 3, 4. At 0, the x of n is equals to 1 over 2 to the power 0, which becomes 1. So the first value will be at 1. Then the next value will be at 1 over 2 to the power n becomes a half, which will be there. The other one becomes a quarter, and becomes an eighth, etc. So our function might follow that route, and that is how you define a possible way of defining a discrete time signal. And alternatively, you can define a discrete time signal using the list of sequences. And we are using some notation here that I'm not sure if you are conversant with this, that you have an arrow that is pointing to one of the value, one of the list of values, and that value simply says when n is equals to 0. So we are saying that at this point n is equals to 0, and now you can say that your x of n takes these finite sequences of values. So for instance, if this arrow says that this is 0, then this is minus n is equals to -1, n equals -2, -3, etc. And on the right, 1, 2, 3, 4. Therefore, if you are to represent this signal on a graph, we are saying that this is 0, 1, 2, 3, -1, -2, etc., -3. So we are saying that at 0, our signal, which is x of n, I can use a different color, is going to be 1 at 0. Then it's going to be 0 at 1, going to be 1 at 2, is going to be 0 at 3, and I guess 2 at 4. So I think these are the values that, I think this is a 4, 4 plus 4. And -1 is going to be at 2, so our value is going to be there. So I'm just using the simplest way to illustrate that what this sequence can mean. And the next sequence is another +2, and another -3 is another positive. This is the other one is now 1. So that becomes the representation of that signal in time. So this becomes the representation of that signal right there. So that is one way in which you can represent that signal. And the other method is using the equation like we have seen expressed at number 1 here. We carry on. So we have just said that we use the notation that some probably you may not be conversant about, that the arrow denotes the term in which n is equals to 0. And in case that arrow is missing, therefore we are always going to assume that the first element, the first term, it represents n is equals to 0. So if I represent a sequence x of n that it doesn't have any arrow, like say 2, 3, 0, 1, 2, without an arrow anywhere, then you take that this n is equals to 0, 1, 2, 3, 4, and then you can be able to represent that signal on a typical discrete time scale. So much regarding the discrete time and analog time or continuous time signal. Therefore, we are ready to carry on, and we discuss now the other classifications. And I believe you have met this before, but needless, we will still go through them. And for the analog versus digital signals, we are saying that a continuous time signal, x of t, can take any value in the continuous interval a to b, where a may be negative, may be minus infinity, and b positive infinity. And then that signal is classified as continuous time. It can take any value. Again, there is some cross similarity because between analog and continuous time. But for our definition, we are saying that the signal that takes any value in a continuous interval between A to B is considered to be analog signal. And the other hand, if a discrete time signal x of n can take only a finite number, and actually have highlighted the finite number of distinct value. So we are saying that we have distinct value. Then these are the two characteristics that characterize a digital signal. So that should be well noted, that a continuous time signal, when it takes any value in the interval between A to B, and A might be negative infinity and B positive infinity, then the signal is said to be analog signal. On the other hand, the digital signal has finite number of distinct values. Distinct values are, and when I say distinct values, probably I should say discrete means, I think I should illustrate that. Someone might ask you the difference between discrete time signal and digital signal. What is happening to my screen? Yeah. So if I was to do the difference, is that we are saying that discrete time can take any value, which might be, they are not in a defined range. So this might be 6.27, this might be 4.31, this might be 2.11, this might be 1.00, etc. But this is the one that we are characterizing as discrete time. On the contrary, we are saying that a digital signal has a distinct values that it can take. So for instance, you might say a binary digital signal can take only probably two values, 5 positive V or negative, not negative, but rather 0. So it might only take two values. So it might be positive 5, 0, positive 5, or 0, and another positive 5, then another 0 here, etc. So this kind of a signal, as much as it is discrete, it gets qualifies to be called a digital signal, because the range of values that each signal value can have is defined, whereas the range of values that the discrete signal is not defined or not limited to some specific values. Okay, so we carry on, and now we discuss about real and complex signals. And I normally like to take some breaks between sessions, particularly take a grab of water. Carry on. One person is always sufficient. So let's carry on and discuss the real and complex signals. Just a minute. As I grab a glass of water, well, I'm never able to keep on typing on chat as far as I'm teaching. So I normally recommend that if someone mentions something that you can be able to respond on your head, I really prefer that. So now I'm hearing Lalai saying that there's low volume. I still think that my volume is normal. Increase on your head, Lalai, and you'll be able to hear everything as clearly. Someone can still confirm to Lalai that the volume is okay. My mic volume is actually maximum. But can we check? Check the mic volume. Yeah, my mic volume is actually maximum. So troubleshoot the stuff on your head, Mr. Lalai. Yeah. So thank you, Mr. Verol, for telling them that the volume is okay. Yeah, sometimes communication that comes from students sometimes is bound to confuse people. Because sometimes problem is actually on the student side more than it is on my side. What I tell myself is that if the 90% of students are okay, then the problem is more or less a problem on the student side. Yeah, thank you so much. So I think we are good to go. So we want to discuss the bit on periodic and non-periodic signals. So then before we move on to our last section, actually the energy and power signals is the last concept we are going to discuss today. But before we do that, I grab a bottle of water or a glass of water. Any question or comments? If there is none, you can comment. This is something that you can continue. Actually, I've learned something else. I want to be knowing who are following up, or those who have left the class. This is a small pool that asking you if you are there. Then asking you, can you continue? If you just say yes or no, then I will know that you are following. If I see you're not responded, I know you have left your phone and gone. So I'm launching that pool. Just confirm that people are following the class. The pool is running. Let's pod. Let me see how many people are there. 12, 13. So clearly there are some people who have left their phones and their laptops and they have gone. But I can see a question from Rotich that he's asking, how is the assignment submitted? Don't worry, I said it is going to be on Google Classroom and you will be able to, you can even draw it using on your book and then scan it and then send. So once I send you the task, you will be, you have an option of responding. So don't worry about that, Rotich. Exactly, as I thought, there are about 13 people who have responded. The other 5 are not anywhere near their class. So let's continue.